Hey, this is Jake. Just going to go over the lab here, lab 4, which is an AHB UART implementation, and it kind of combines the VGA and then the previous AHB decoder and multiplexer implementations we have from lab 3, lab 2, and lab 1. So here in general, we have the overall Vivado structure where we have our new UART subtree here with the constant baud rate generator file, and then everything for our transmission and our receive FIFOs and handshake signals. So some of the tasks of the lab are to add parity. So this is just essentially just changing the data for where, if we specify even parity and we send something like 0x55 and it's, that would be a 0, 1, 0, 1, 0, 1, 0, 1, which should have 4 ones. For an even parity, that 9th bit would just be a 0 to keep it even. That way we know that when the receiver gets that data and if a bit is flipped somewhere, it's even parity and it sees one of those is odd, that knows that there's some sort of corruption going on. So another thing we were supposed to do is change this baud generator file to actually support multiple different baud rates. So the way you would do that is you kind of just create a different peripheral. So how I did that in my original Vivado file was I just added this to the AHB UART main file, which essentially sends this baud div reg to 162. That's like a default value if we're not actually trying to write to this 08 address space from our ARM assembly. So that defaults it at a 19200 baud rate, which is what we had set previously in the hard-coded baud rate Verilog file. And then all you really have to change in that baud gen file is instead of inputting nothing and just the clock and reset, we actually input this baud div, which is then changed, and we do the same math on that we did previously. So there's not much change in the baud rate generator file. Then to write to it, we can just, in our Kale here, we assigned this, as you can see up here, to have 0x510008 address space. So we load that constant into R0. Then we load 325, which I used just an AI to calculate. That should be around 9600 baud rate. And then we, of course, store that value of 325 at the address of 0x51000008. And then that will then effectively change that baud rate in the Verilog file. So then for parity, it's essentially the same, not the same thing, but it's a similar type of change where you have to go inside the Verilog file, and we're looking at the existing 8-bit data frame. And now we're just adding some logic to append this parity bit based on if this data in has even amount of ones or odd amount of ones, and if we have selected odd parity or even parity. So depending on this just kind of simple case statement, we're able to either flip that bit 0 or 1 depending on whether it needs to be odd or even parity. And then sending and receiving files via UART. Let's see, let me just do a quick demo here. So to do that, it was essentially just creating a quick ASCII read loop in the ARM assembly, and then you can just use a putty send file thing, which serializes it and sends it byte by byte. So like I had this text file right here in SGSU file 26. So it's just a UART text that is a test send, and then we see that come over on the putty terminal. For some reason, that implementation that I had was broke, and it's just taken me so long to get it back working. So I have parity and I have everything else, but I just didn't want to implement that again. But I have the the screenshots of when it was working here for my report, and I explained it. So this is the kind of the file that I had, or the ARM assembly loop that I had going with my previous DRAM instruction set that broke the bitstream somehow, or that broke the entire design. I don't know what happened, but you're essentially just waiting to receive a character, then you send it, we draw it, and we just continue to repeat this loop. Right, so it's pretty straightforward. Yeah, so in general, let's see if I'll just do a quick demo of like the lab working. So we have COM3 open, and then I'll just program this one more time with the reflashed bitstream. Let's see, boom, and then I think I can pull this up. So first of all, obviously you guys can see the terminal now says Jake because I changed the ASCII characters that we're writing to this FIFO at the beginning here. And then if I just go to my second monitor and go to HDMI 2, yeah, so we can see in the top, wait, why is this is backwards, guys, I'm sorry, this is hard. Okay, so we can see Jake, and then as I type in, we can say, you know, backspace, backspace. You can see that's represented by this caret up, and then I can type test space Jake. Yeah, so everything is working as you'd expect, but yeah, in general, this lab was pretty finicky, and it was very hard to get everything working. And I'm not 100% sure why. Just with the different Vivado versions and everything, it kind of became a challenge. Okay, thank you.